There, an 80 Newton force has been applied to a block and moves it 20 meters along the direction of the force. How much work has been done to the block? Is that right?
Yeah.
So sometimes it's good to draw a picture here. I'm gonna do that for you here. So we got a block, we got an 80 Newton force, and we're moving it. It moves distance of 20 meters.
Okay.
So the work is, one definition of it is force times distance. And the force in this case is 80. The distance is 20. The force has to be in newtons and the distance has to be in meters. So it's 1600 newtons times meters, or what's more common is joules for that. Is that okay?
Sounds great.
All right.
Very simple. Thank you.
Yeah, it's pretty straightforward for the first one. We'll see where it goes from here. So for the next one here, calculate the work done when a 20 Newton force pushes a cart 3.5 meters. This is exactly the same. Work is force times distance, which is in this case 20 newtons times 3.5, so it's 70 joules. No image needed here. We're
Awesome. Number 3.
So the 3 is asking about vertical motion, and it's similar to the you've got a 360 kilogram piano. Okay, it has a force down, mg, and we're going to move it up 10 meters. So the work is still force times distance. The force, though, in this case, we have to calculate. The force is mg. It's the 360 times 9.8. So you can get that value if you want, but we're going to just put that value into the equation over here. It's 360 times 9.8. That gives you the force. The distance is 10. So we'll multiply those 3 together, and we'll get
together in the calculator. So we got 360 times 9.8 times 10. So I get 35 to 80.
35 to 80.
Is this in joules?
Yes.
Perfect. All right. I'm guessing these are going to get harder now.
They do. This is a good worksheet though, because you can do the first few that are pretty straightforward pretty quickly, and then now it's like, okay, well, do I understand what's happening here? So if a 100 Newton force has 30-degree angle pulling on a 15-degree block for 5 meters, what's the work? So the picture here would be pretty useful to have. I've got to make one up here. The 30 degrees is assumed to be in the direction of motion. Okay, this is a 15 kilogram block, and we're moving it 5 meters. So one of the things that I didn't tell you completely is work is force times distance cosine of the angle between there. So in all the problems we've done so far, the angle has been
irrelevant.
Well, it's been 0, and you might think, well, if it's 0, how can this work? Well, the cosine of 0. This is all kind of a side point over here. The cosine of 0 equals 1. In other words, the force and the direction of motion are the same.
Say it one more time.
The force, comma, the direction of motion are the same. So let me scroll up and try to explain what I mean by that. In the first problem, your force is going to the right and it moves to the right.
True.
Those are in the same direction. Is that not clear?
It's clear.
I mean, you're going to the right, and then you're pushing it to the right, and your force is directly to the right. In
Okay.
the third problem, the force is going down or up in this case, and that's in the same direction as motion. Which I know it says you're lifting it. The other point here is that the cosine of 180, which is when these are opposite, is -1. Um, but you can play around with the signs here a little bit. I'm kind of tripping over my words because I realize it's not quite correct the way that's written, but so in this problem, there's a couple of ways to do it. The way that the way that they probably want you to do this is to just use the formula. The
Work equals
formula
force times distance,
is
right?
100 times 15 times cosine of 30. But I think I want to give you a little bit more information, but we'll probably end up doing it in another question. Not sure though. Did you get a
Excuse me.
number for this?
All right, so 115 cosine 30. Okay, 30 for the angle, and 15 is the weight, right? And
30 is the angle. 15 is
oh, never mind, 15.
I'm
All right.
sorry. The distance is 5, not 15. So this should be 5.
Okay, doke. All right, so 100 cosine 5, 105 cosine 100
No,
times 5.
it's yeah, 100 times 5. So it's 500 cosine 30.
So what I get is 77.125.
Is your angle is your calculator in degrees or radians?
Must be in radians then. Yeah, it's in radians. All right, let me copy that again. All right, 433.01.
So about 433 joules.
All right.
Okay. Now, in this type of problem, what I would normally recommend is converting this into the two angles that you already have. And then you only have to find the work in the direction of motion. So like there's no work vertically. And because you're moving it to the right. So there's no work in the vertical direction. I don't know if that matters in other questions here. So I guess I need to hold off on going into more detail. We'll see what happens there. And I guess I went to 5 instead of 4. I'm sorry. I just caught that now as
That's
well.
okay.
We'll go back
And
to
work
4.
is just 433 joules, and that's it, right? That's the whole
That's it.
problem.
Yeah, that's
Okay.
it. That's
All
it.
right. Let's go on to number 4.
All right. A box rests on a frictionless surface. A girl pushes a box the force of 18 newtons to the right, and a boy pushes on the box the force of 18 newtons, or sorry, 12 newtons to the left. The box moves 4 meters to the right. Find the work done by the girl, the boy,
Boy,
and then
and the net force.
yeah.
Okay.
So the work done by the girl, she's pushing with 18 newtons, and it goes right 4.
Okay. Oh, so the girl, so the girl has more force than the boy, and
Yeah. So the
she pushes
girl,
it 4 meters to the
yeah,
right.
her work it's still force times distance cosine theta, but it's 18 times 4 because she's going that direction. The picture here actually it does, there is some importance here that this is the 18, this is the 12,
32 joules, right?
yeah, in joules.
Okay.
The boy work is force times distance. Now its force is going to the left, so it's actually -12.
Oh,
But and it still moves 4 meters to the right, so it's -48 joules. The net force is the addition of the two of them, so it's 72 plus -48. So it's 24. I'm sorry, I'm doing this completely wrong. It's 18. I'm not erasing. It's 18 to the right, 18 newtons to the right, minus 12 newtons to the left.
oh, 18 newtons to the right. Okay. 18 newtons minus 12 newtons. Wait, how's that 18 newtons minus 12 newtons again? Oh,
You got 18
yeah.
to the right, 12 to the left.
Oh, okay. I got that. So net force in
Is
this case
six,
is
six,
6.
and really it's 6 to the right, which is important to say.
All right. On to number 6. Calculate the power expended when a 500 Newton barbell is lifted 2.2 meters in 2 seconds.
All right, I got to remember the formula for power. I think it's work over time or work per unit time. Do you happen to have it in your notes? I think it's work over time. Yeah. So power is equal to work divided by time. So it's an extension of work problems. Notice that they haven't given you any time, but they all of a sudden give you time. So the work is still force times distance. So the force is 500 newtons.
Okay.
It's lifted 2.2 meters. So that's our work. That's
2.2.
1100 joules. So the power is 1100 joules over, and then it has to be time is in seconds. So work is in joules, time
It's
is in
going to be
seconds.
joules by second. Is this going to be like, was it 6? No. 550
Yeah,
joules per second?
it is, but that's also referred to as a watt, I believe. So you're gonna have those units there. This is where they start to not mean much. It's like, what's a watt? Well, it's a joule per second. What's a joule per second? It's a force. It's a Newton times meter per second. Not always the um, the easiest.
Mm-hmm.
Okay, back to
Number 7. Escalator is used to move 20 passengers every minute.
from the first floor to the second floor. The second floor is located 5 meters above the first floor. The passenger's average mass is 60 kilograms. Determine the power required of the escalator in order to move this number of passengers in this amount of time. Every minute. So that's 60 seconds. Okay. So here's what's going on. You've got a box full of passengers, and it has an mg.
Yeah, of course.
It's 60 times 9.8, but there's 20 of them. Okay, so that's the total mg here. So this is the force due to gravity.
60 times 9.8 is 20. Okay.
It's moved up 5 meters. So the work is whatever this number is, which I should be doing the calculations as well. We're getting into that area of physics where it's the answer is not as important as the intermediate steps. So the fact that if you do or don't get the right number here doesn't matter to me. I know it does to the instructor, but what we're trying to emphasize is how to do the problem. So you find the force. That's the force there. The distance is 5 meters. So we can get that number as well.
So 1170, 760, is that joules for force?
Newtons.
Newtons? Okay. This is newtons. All right, so then we get work equals FD. 11, 760, 55 equals 800 joules. Is that the whole thing? Or do we have
That's the
more
work.
steps?
What is it asking for? The
What is
power.
the power? Okay.
Power is equal to work divided by time. The work in this case is 58,800 joules over your time is 60 seconds. So notice, you could do this all in one step, but
Oh,
that's,
every minute. Okay. And
yeah,
that'll be watt and watts, right?
that's right.
58,800 joules over 60 seconds. And that equals 980 watts. Okay. On to number 8.
Yeah, I heard some things fall. Hope everything's okay there. Yeah, we'll keep going here to number 8.
Those are
500,
messes with this chapter fun.
500 Newton force is applied to an object if the object travels with a constant velocity of 20 meters per second. Calculate the power expended on the object. So I believe there's another formula for power that has to do with velocity. Um,
Velocity, okay. Oh, we're back to what we're
so
doing.
so power is also the force times the velocity.
Okay.
Now, why does that work? If you recall, work is force times distance.
Yeah.
Power is work over time, force times distance over time. Distance over time is velocity. So that's why you can get back to this
Cool.
relationship. So the power, yeah. I mean, it's handy, but I mean, I don't, I could, I'm going to ask the guy that I know that helps me if he really knows this formula.
500 times 20. That's it?
Yes.
Just the power expended. Okay.
I mean, the answer, I mean, this, like all of this on the right is like, you have to know that to do this. If this were a multiple choice test, I would give you 500 times 20, 500 divided by 20, and maybe some variations on that. So you'd be guessing. So you have to know the stuff on the right, I guess is my point.
All right. This is in watts, correct?
Yes. So if maybe your parents have an energy bill that they will show you, it's in kilowatts, and you may want to take a look just to get an idea, like what not the cost, the usage in your home, because it sometimes doesn't translate to. But there's a figure there. It'll say like you used 637 kilowatts last month. That's the power. All right. 9. Are we up to 9?
We sure are.
Okay, we're up to 9.
9 is placed in a weird angle for me.
Say that again.
Just that 9 and 10 got labeled weirdly.
Yeah, I said I modified it on my side. So an elevator must lift 1,000 kilograms a distance of 100 meters. So what you should start seeing is like, oh, that's kind of force. Hang on a second. Okay, so we did do that up there. Okay, sorry, I thought we didn't include a calculation. What is the average power the elevator exerts during this trip? I don't know why it's called average power. You may want to ask your instructor. Again, I'm not a physics expert, but you may want to ask if average power is equivalent to power.
Average power is equivalent to power.
Yeah, but I'm because he wrote it differently. I assume it's a guy, but that may be an assumption too. So let's draw a picture here. You've got 1,000 kilograms. Mass equals 1,000 kilograms, and you're going up 100 meters. Okay, and the velocity here is 4 meters per second. Okay, so the power is force times velocity. We have velocity. Sorry, 4 meters per second. The force, though, is 1,000 kilograms times 9.8. So it's 1,000 times 9.8 times 4 is your power. Now, average power, let me check. It might be power per unit distance. Let me see here.
I have if you just type it into the search bar, for some reason Spark Notes just shows up right away and it has an answer for it.
What does it show for the power formula or average
This
power?
Since the work done is easily calculable, you get 9.8 times 10 to the fifth joules. The total time of the trip can be calculated by the velocity of the elevator, 25 seconds. Thus, the average power is given by power. P equals W over, can't use that. A equals 3.9 times 10 to the fourth watts, or 39 kilowatts. It's, for some reason, it's so blurry. I don't understand why it's doing that. Let's see if there's another. Let's see.
So I still stand by that this is your answer.
Uh,
But I don't know for sure. So I mean this is where I want you to get the the best grade possible, but I also don't have a good reason to tell you to not use this formula. So you're gonna have to either check with your instructor, or I'm trying here to find something. But average power is a concept that's used in electricity and magnetism that isn't really reasonable here. But I'm seeing work per unit time, which is the same as power times or force times velocity. So I'm gonna suggest you go with this one down here. So that's 39,200 joules. Or I'm sorry, watts.
Alrighty, on the number 10. Let's see. The floor of the basement of a house is 3.0 meters below ground level, and the floor of the attic is 5 meters above ground level. What is the change in potential energy if a 2 kilogram object in the attic is brought to the basement?
The potential energy, I write PE, is defined by mgh. So the mass is the mass that's given.
Mhm.
G is 9.8, and height is the distance that it's um, moving. So it looks like there's a ground level, and it starts like 3 meters above it, and then it goes down 5 meters below it.
Okay.
So it's the total difference in height. So it's whatever you start at, whatever you finished at, which in this case is 8 meters. 3 plus 5.
So potential energy equals what is it again? Mg.
Mgh, mass times gravity times height.
Oh, okay. 2 times 9.8 times 8 meters. All right. And then we get, let me put that in my calculator, 9.8 times 8 times 2. I get 156.8.
156.8, and potential energy is in joules. So the reminder here is that work is the same as energy, which is in units of joules. Power is in watts.
Oh, okay. I'll remember that.
So remember, and there's several formulas. It's work per unit time, or it's force times velocity. Okay, moving on to 11.
Yes, sir.
See if you can do this one on your own. I'm going to step back. I'm going to just step away for 60 seconds, and then I'll say hello when I'm back.
Sounds good.
Same formulas before. Hey Jack, I'm back. Have you been able to work through this?
Yes. I end up getting 56.84 meters.
All right, so potential energy is mgh, and they give you the potential energy, 145. Its mass is 5.8. We know g is 9.8, so you're just solving for h.
Wait, my bad. I did it incorrectly. I got 2.55 meters.
Yeah, 2.55. The height is 2.55 meters from ground level. Good. Okay, let's keep this going here. We're on to number 12. Number 12, a man climbs.
So this is just pretty easy. All right, I'm gonna try to set this up. So we got 68 joules equals what is it? We got height 3.6. We don't have mass, but we do have gravity, which is 9.8, and then multiply that by m. So divide that number 3.6 times 9.8. That's 35.28. Divide that 2268 divided by 3, 35.28. So let me get this 2268 divided by this number. And I end up getting 64.29 grams.
Kilograms.
Kilograms. Oh, kilograms. We're doing kilograms. Forgot about that. Kilograms.
All right. The next question is going to be a different kind of energy. There's several different kinds of potential energy. One of them is potential. One of them is a spring. So spring potential energy is a different formula altogether. It's 1/2 kx squared. K is the spring constant, and it has units of newtons per meter. You'll see that I do that in brackets all the time. That's my convention. It's not one that I see. And then x is the distance that the spring is stretched, and it's also in meters. Sometimes, well, not sometimes, very often they give you the spring is moved like 10 centimeters and you have to convert it to meters. So how much force? Oh, this one's asking about force. I'm sorry, I didn't even catch that. The force equation, F equals kx. And it's the same set of units here. So the force here of the spring is it's 377.16, and the distance it's stretched is 0.39. The force will be in newtons.
39. All right. And that equals, let me get this. 377.16 times 0.39. I get 149, 147.09. What is this? Going to be in newtons. All right.
So Jack, just a reminder here, you really want to have your base unit downs. Like mass is always in kilogram. Time is always in seconds. Distance is always in meters. Forces are in newtons. Work is in joules. These are the base units. Like sometimes at the beginning of your class,
watts, right?
Yeah, powers and watts. But you really need to know these so that you know like what you're looking for and what to convert between. That's just a an aside recommendation here. So we'll move to 15.
All right. 15. Wait, 14, right?
14. Yeah, I keep doing this thing where I want to go way ahead. So I'll slide this question down and we'll move. We'll go back to 14.
Okay.
It requires a force of 594.55 newtons to stretch a certain linear spring 0.15 meters. What is the constant for the spring? If you know the equation, it's pretty straightforward. F equals kx. You're solving for k, so k is equal to F divided by x. The force is 594.55 over 0.15. One of the things that about the spring constant is that it's usually a really large number, and we don't really understand it other than like when it's given to us, but it generally has to be quite large to do what it's supposed to do.
3963.7. What's the unit for this?
So K is in newtons per meter. You can get that from the units of force. The units of force is in newtons. The units of X are in meters.
All right, on to 15.
All right, Vincent's mountain bike has a spring with a constant of 64 newtons per meter. So that's the 64 newtons per meter. That's your K. And it compressed 0.17 meters when she hit a bump. How much energy does the front spring now store? So the front spring has potential energy. I wrote this in earlier equation, 1/2 kx squared. You definitely need to know this. So your potential energy is 1/2 64.17 squared.
0.17 squared. Okay.
What did you get for an answer here?
0.2.
Let me check you on that. Just seems really small, but
Small.
when you square 0.17, it definitely gets small. So I got 0.9248 joules.
Awesome.
Okay, 16, 17, 18, 19. Okay, so we should be able to get through all of these. I'm shocked the instructor is able to come up with these. Well, oh, you said you found them online, so I guess I'm giving them too much credit.
Yeah.
They're coming up with their own material. Spring has a potential energy of 22.14 joules and a constant of so they mean a spring constant because it's newtons per meter. How far has it been stretched? So whenever you're given energy, your formula is potential energy of a spring is 1/2 kx squared. They're giving you the potential energy because it's in joules. They're giving you K, 676.96. They are not giving you x squared, so you have to solve for x in those problems. This is where you got those skills from math where you're going to be able to solve and take a square root and get your answer here. So go ahead and work that out. See if you come up with, or let me know what you come up with. I'll be entering the getting this as well into the calculator.
Here we go. There's 1/5 times 6. Wait, yeah, 676.96. And then 22.14 divided by this heap's number. What square it is. It gets very small. I get 0.2557, whatever.
So I get 0.0654. Did you take a square root?
Yeah, I did take a square root.
Okay. Check your calculations to get rid of the 1/2, or you can take a half of this number. Any of those are fine. Oh, you know what? I have the error on my side. I have an extra calculation. So I am in error here. Let me, it was exactly what you said. X equals 0.256, and that's in meters. All right, we're up to 17.
Yes.
Okay, so we're moving to kinetic energy. there's several different types of energy that your instructor is giving you in this problem set here. Kinetic energy in this case is 1/2 mv squared. There are other types of kinetic energy, but this is the main one. So just as a reminder, the potential energies mgh, potential energy of a spring is 1/2 kx squared, and the kinetic energy of an object is 1/2 mv squared.
So we got velocity, which is 2, and we got 3 kilograms. So I can just set it all up. In this case, I just get 1/2 times 3, and 2 square, which is 4. So just 1/2 times 3 times 4, 12, 6 equals
6
6
joules.
joules. All right, so that's probably the most simple one that I'll get.
Yeah, it's nice, but we'll see what 18
that.
says here. If determine the kinetic energy.
How come potential energy has 2 formulas there?
Well, one's for a spring.
Oh, spring potential energy? Like
Yeah.
Okay.
Maybe your instructor will call it something different. I just always say PE because it's clear for me. I mean, some of these are my conventions. I mean, they're I don't pretend to try to conform to what they do in the schools, but try to do what makes sense to do the problems as easy as I can. I think you'll see U, they'll say US or UP. I think those are standard, but
So kinetic energy, same formula for A.
kinetic energy, 1/2 mv squared. So you got 1/2 500.
20 squared. That's like 400 or something, right? So 250 times
Yeah.
400.
Yep.
All right, so 250 times 400, you get your 100,000.
100,000 joules. Okay.
Oh, that's a lot. Oh, 500 kilograms. That makes sense. For A. All right, now we got B.
If the roller coaster were moving with twice the speed, so
What would be its new connected? All right, so twice the speed would be 40. So I got kinetic energy equals 1/2 times 500 times 40 squared, and that's like 1600, right?
yeah, it's a lot bigger now because of the fact that you're squaring velocity. So velocity is more important than mass in this example.
1600 times 250, I get 400,000 joules.
Yeah, so it doesn't double, it quadruples.
Perfect. All right.
All right, last one here for this physics problem set. Okay, so this is a working backwards problem. The kinetic energy is 1/2 mv squared. You got 1/2 40 and v squared, and they give you the energy on the left, so you're solving for that value.
And kinetic energy was it again? 1/2 mv squared.
1/2 mv squared, yeah.
Okay, so we got that kinetic energy, which is 12,000. We got 1/2. We have our mass, but we don't have our velocity.
Yeah, that's what's asked for, speed in this case.
So v squared. Oh wait, isn't velocity different than speed?
Well, speed is the absolute value of velocity.
Oh, so it's still the same thing.
Yeah, you end up getting plus or minus for velocity, but you can just take the absolute value of it.
Divided by 20, divided by 20, 12,000, divided by 20. You get 600. 600 equals v squared, square root, minus square root of 600. In this case, it's like 24 point whatever. So velocity equals 24.49. Oh wait, I need to get some more room for this. Velocity in this case equals 24.495 meters per second. Not meters per second squared, right?
Nope, that's acceleration. So
That's everything I wanted to work on today. Thank you, Matthew.
You're welcome. I'll send out the notes and the recording here shortly. Thanks again for scheduling.
Have a good day, Matthew.
You too.
Appreciate it.
Bye now.